So at the end of this lecture, you should know how we control the temperature in bioreactors. So what kind of options you have, how expensive they are, and how you select what's most appropriate for what you're doing. And what you have to take into account here, that even though it's all about controlling the temperature, in bioreactors it's very important that you sterilize your batches. So you need both cooling, but you also need heating. And there are two main methods that we can use. We can have like an external jacket, which is a pipe, and then we have internal methods where you have coils within the reactor that are more effective, but they are a lot more expensive. Plus you can get issues with sterility there because they're very difficult to clean. And here you can see what these different options actually look like. And if you remember from the design of heat tube exchangers, you would always have baffles because they help to appropriately distribute the heat throughout the reactor. On the left you can see what happens if you have a jacket around it. Then the middle one is where you have this helical coil, which was more effective at heating but more expensive and more difficult to maintain. But another interesting option, which is specifically for bioreactors, is where you don't use the baffles but you use the heating coils that also act as baffles, which is from an energy perspective a very interesting option because you do both at the same time. And the main reason why these baffles are so important is just by looking at the general formula for heat transfer, as you know. So you know, obviously we can't change U, so that's dependent on other parameters. And then the delta T in general tends to be quite small because that's the difference in bioreactors, since you tend to look at actually rather mild operation conditions, so relatively low temperatures. So if that means delta T is small, the main thing you have to play around is to change the area, which is why you really need these baffles in order to increase your heat transfer. And while the formula from the last slide seems quite straightforward, it's not that easy to calculate the heat transfer in bioreactors. And that has to do that, like when we look at the heat, it's not just the agitation that we look at, which is normally the case, but we will also see that when these microorganisms grow, that they produce a lot of heat. So we definitely need to take the growth into account. So that means that if you want to kind of estimate what your Q total is, you first of all, when you look at the agitation, you see this in watts per liters per hour. You will see that this will depend on the power number. So it will look at how fast your agitation is. So we'll take these things into account. It will also depend on the volume of the reactor, obviously. But then you will see the Q growth depends on how much oxygen is available. So how fast can these microorganisms grow? And again, it will depend on the volume. But if you would actually sum up these two terms, you would see that they're not consistent in units. And this is because this is more or less an empirical formula. And you need some kind of correction factor. So it's not an equation that's suitable for the design projects where you can look into more detail. But this is actually a very quick estimate that if you want to know what Q total is, you would sum up these two contributions. But in reality, all you can really do is measure it. So there will be, if you look at the rest on Cantons, you will see there's an example exercise where you will show how we can determine Q total empirically and also how you can correct for the units that are in this equation. So roughly in this lecture, you should know what different methods do you have to control the heat. So what different coils and jackets there are to control the temperature and have an idea of how you can determine the heat transfer within bioreactors.